them 2.1 notes. However, that was really not that accurate. It really should be at our 2.2 notes because I'm trying to redo the way that I structure everything based on that course description that AP put out because they broke it down into units. So as I went through this stuff, I really wish I had taught this first before I taught you guys what I taught you on Friday, just because I think it might make a little more sense that way. So what we're going to do, we're going to go over this today. Tomorrow we'll probably do like a quick review of what we learned on Friday, which really I should have called those 2.2 notes. And then I'm going to try to proceed according to the AP plan there for that. So today we're going to be talking about average and instantaneous rates of change. We've already talked about this a little bit when we were doing limits. We've talked about how we could sort of estimate speeds based on tables that we've looked at. So here is an example that is not a calculus example. This is an example that you really, you might do it even in middle school. It's nothing special about this problem. So I'm just going to give you guys a couple minutes to look at it and answer this question. If we need to find the speed, we need distance divided by time, miles divided by hours, right? So for the top part, we need the number of miles that this person traveled. That's fairly easy here, right? We just need to do 73 minus 9. That's our top part. And so 73 minus 9 is going to give you 64 miles. And then on the bottom we need hours. There's a few ways that you could do this. How much time has passed from 5:22 to 6:33? 1 hour, 11 minutes. So I have to divide this by so many hours, right? I can't do 1.11 because 1.11 is not 1 hour and 11 minutes. So how do I change that 11 minutes to hours? So if you use unit conversions, like from chemistry, 11 minutes, we want to change our minutes to hours. So minutes goes on the bottom, hours goes on the top, so that the minutes will cancel. How many minutes equals an hour? 60 minutes, 1 hour, so we would get 11 over 60 hours. So we could just do 11 divided by 60. Sometimes you know what to do in your head. Like if I'm telling you that we had this conversion in Math 1, I gave them a football field and I told them it was 100 yards by 160 feet. And had to do Pythagorean theorem to find the length of the diagonal. And so the whole class got it wrong, as I knew they would, because I gave them yards for one side and feet for the other, and I didn't point out that I did that. I just gave them the problem. So I knew they were all going to miss it. And they did all miss it, except for maybe one or two who just were embarrassed to even say they had something different because everybody else had got a different answer. So then I tried to get them to figure out why it was wrong. And we did not get very far on them ever looking at the units for that. So eventually I had to tell them why the units are wrong. So like if oh yeah, that's 160 feet, I need to change it to yards, I'm going to divide by 3. Sometimes it's really easy for us to think of what to do in our head. Sometimes it's not, or sometimes our brain is just not functioning properly, and we have a hard time. So you can always set up a unit conversion for something like this if you're having a hard time deciding what to do to change from one to the other. So if we do 11 divided by 60, that is going to give us 0.183 repeating, so we could say this is 1.183 repeating hours. And really, we could show where we subtracted here, or we could just do 1.183 repeating there. So if we do 64 divided by 1.183 repeating, we are going to get 54.085 miles per hour, so about 54 miles an hour. Okay. So that is the average speed that Jennifer traveled from mile marker 9 to mile marker 73, okay, on I-77. So this is maybe something you might have not converted right or might have messed up, but this is just basically distance divided by time that you've done for a long time. So what I want you to start thinking of here, that we kind of talked about at the very beginning of the class when we were talking about my speeding tickets, is that a cop does not care about your average speed, right? They care about your instantaneous speed. So if we think about this situation, based on what you know about I-77, which runs from here to Charlotte, based on what you know about I-77, from 9 to 73, 9 being just right down there around Charlotte, 73 being on back, 73 is 420 is the 421 exit, I think, isn't it? I think it's 73. It's close to that if it's not 73. So, so coming back to Elkin at 5:22 p.m., do you think that Jennifer went 54 miles an hour all the way back? Probably not, because the speed limit's 70 miles an hour on 77. What's more likely that happened in this situation? There were times when she slowed down. Probably in this particular case, based on my prior knowledge, she was stuck in traffic in Charlotte and was going really slow, or possibly even stopped some in Charlotte. And then she went 70 the rest of the way home once she got out of traffic, and that made her average speed a lot lower than 70 miles an hour. So while the average speed tells us something about Jennifer's trip, if we really wanted to know about Jennifer's trip from Charlotte back towards Elkin, it would probably be helpful to know her instantaneous speed at different times. So exactly how fast. So at maybe 5:32, she might have only been going 15 miles an hour because she's stuck in bad traffic. Whereas at at 6:27, when she's almost back this way, she might have been going 75 or 80 miles an hour, although she shouldn't. She might have been. So average speed versus instantaneous speed can give us different pieces of information. This tells us that she was going slower than she could have been on that stretch of road based on what we know about it. But it doesn't tell us when she was going slower or how much slower at a particular point. So it gives us some information. If we had access to instantaneous speeds, that would give us more information. We could answer questions like, where did she get stuck in traffic at? Was she speeding at any point? We could answer those sort of questions. So we'll be looking at today average versus instantaneous rates of change, which speed typically we think is a rate of change, but it doesn't necessarily have to be speed in order to be a rate of change. So here's another example that we've got. So the AP exam loves to do this. They love to give you a situation, and then they will use a lot of T's and F of T notation to ask you about it. Because if I just gave you what is the average rate of change of F of T on the interval 0 to 4, explain this rate here, that's, they could have just given us the equation or a chart, but it's important to know what everything stands for here. So a function F of T gives the number of students who have voted for homecoming queen as a function of time T. So time is measured in hours since 8 a.m. So the T right here, they just put a T on here, but I could write this is hours since 8 a.m. And then, what does the F of T stand for? Number of students who have voted, right? So number of students who have voted. So when you see this rate of change, that should make you think slope. Back in Math 1, whenever you learned about rate of change, slope is what you were finding a lot of times. Okay, so our slope, we know, is our change in y over our change in x. And so we're only looking on the interval from 0 to 4, so we really only care about these points right here on the graph. So if we want to find that slope, we would take, this is like the point, we've got the point 0, 35, and our other point is 4, 256. So we would just do our slope formula. 256 minus 35, subtract your y's. Delta y over delta x equals 256 minus 35 over 4 minus 0. So that is going to give us, what is it, 221 divided by 4, which is going to give us 55.25. So, looking at this, I've got the slope, it looks beautiful, but I'm asked to explain it in context of the situation. And this is where I see a lot of students falling apart. So, let me show you what I do a lot of times to help me with this. I ask these same types of questions in Math 1. We're still not really to a calculus example because average rate of change is really just a slope. So you can do that even back in Math 1. So I always think this is change in y over change in x. What is y measured in? That line on the table that stands for y, what does it represent? Number of students, right? So it is measured in students. And then what's the t measured in? Hours. Okay, so that means that that top number was students, the bottom number was hours, so this is measured in students per hour. Okay, that helps me a lot in explaining the situation. Because if I've got 55.25 students per hour, well, that kind of helps me see how to explain that answer. So for this, I would say I could say 0 to 4, but 0 to 4 doesn't really help me in context of the situation. Because what does 0 to 4 mean? It doesn't really help a lot, right? What does 0 represent as far as time goes? 8 a.m. What about 4? What time would that be? That'd be 12. So from Justice, you're back. Oh, that usually is a problem. Thank you. All right. So a.m. to 12. Hold on. This is p.m., right? The a.m. would be in the, okay. Should know better. But sometimes that still gets me mixed up. So from 8 a.m. to 12 p.m., students voted at an average rate of 55.25. This program does not like new setup. So 55.25 students per hour. And it's important there to use that word average rate, because this is not an instantaneous rate. Of course, it doesn't make any sense to have 0.25 of the students. But averages don't necessarily have to make sense because they just describe the trend, not the actual number of people there. So that's what this particular instance tells us here. This is still just regular slope through a line. So our average rate of change gives us slope. We're going to do one more. I think these are even more difficult. I do need you to change something on yours. I forgot to change it before I printed it. Make that x minus 2. I think yours might say x plus 3, which gives you way too big a numbers to deal with. So make that a minus 2 instead. Not way too big, just bigger than I feel like dealing with. So typically, this is a lot harder for students than the last two problems where you actually kind of think about the situation. So we want to know the average rate of change of f of x on the interval from -1 to 3. And so I'm going to pull up a graph here that we can kind of look at the graph of this function. And so when we look at the graph of this function, here are 2 points. We've got a point here at x equals -1. So x equals -1, we have a point, and x equals 3, we have a point. And we want to know the rate of change just over that time period, right? So we're really looking at the slope of the line that we have between those 2 points in this case. So in order to find the slope of that line, whenever we find the slope through the endpoints, I'm going to write it this way just because theoretically AP likes to give you these problems without actual numbers in it. They like to use this notation. So -1 f of -1. That is the point at -1. You'll see I actually, on my graph here, that's how I put it in. I put in -1 f of -1. And Desmos will put that point there on the graph. I can change, the way I've set this one up, I can change my function and it'll still put that point on the, it will be on the graph even though it'll be a different graph. It'll be a different coordinate, but it'll be on there. So, -1 f of 1 would be our first coordinate, and then 3 f of 3 would be our second coordinate. So we could find the average rate of change by doing our change in y over our change in x, which in this case would be f of 3 minus f of negative 1 over 3 minus negative 1. So f of negative 1 would be negative 1 minus 2 squared plus 1, which would give us negative 3 squared plus 1, which is going to be 9 plus 1, which is 10. So that f of, that's our f of negative 1. That goes here. And then we'll have our f of 3 is going to be 3 minus 2 squared plus 1, which is 1 squared plus 1, which will give us 2. So that'll give us f of 3 was 2. We just found that. And f of negative 1 is 10 all over 3 plus 1, which will give us 4. So we will get negative 8 over 4, so negative 2. I wrote that down wrong whenever I did this. Oh. Oh, wait, hold on. I started using 3s when I should have. Hold on. No, that's right. I was supposed to use 3. Alright. And I was supposed to use negative 1. Okay, I just did it wrong whenever I read it. Okay. So, yeah, so negative 2 would be our slope. So if you look over here at our graph, what we see is we've got this point from, this point up here is at negative 110. That's our point that we have. And then our point down here is at 3, 2. And if we look at the line that connects those two, then we would have a slope. We would go down 8 to the right 4. So we'd have a slope of negative 2 for that. Okay. So this average rate of change is just the slope for whatever points that you have. So while if I look at, let's see, let me make this show up. Okay. Hold on. Alright, so if I look at, let me move my A over here so that makes sense. Alright, so right here, let's say that I'm trying to find the slope of this particular graph at 3. Not the average, but at 3. You'll see the slope here is negative. Negative, negative, negative. My rate of change is negative for all of this time. But then it switches right here. It switches back to positive. So I have a positive slope as I get closer and closer and closer. So if I'm looking for that point, the slope at that point right there, I would have a much different answer than if I have my average. Overall, it's negative a whole lot more than it is positive as I go from negative 1 to 3. So on my average rate of change, it's going to be a negative rate of change. But at 3, I definitely have a positive slope for that line. So looking at the slope at different points is going to be much different than looking at the average slope over time here. And this would be the case even if I had a different equation for this. So let's talk a little more about that. Let's talk about finding the instantaneous rate of change. So I've made this other graph that's even more generic. And the last one we just looked at. Okay. So does not matter what f of x is. Currently, I have f of x is the square root of x plus 7 over x minus 3. So if I take my x coordinate here, if I want to get the tangent line, okay, that tangent line is going to give me the rate of change, the slope of the graph at that point. If I find that slope at that point, it will give me the rate of change. Then I need this tangent line. So I could do average rate of change, but average rate of change doesn't give me the exact. Oh wait, I'm moving the wrong one. Hold on. I don't really mean to move next. I could do average. I could just pick a point on the graph and do average rate of change. But if I can make that rate of change get closer and closer and closer and closer to that point of tangency where it's just a line there, then that is going to give me the slope of the line at that point. So,
Part of the interruption is a reminder for any ROTC students who have donuts and sold donuts. If you have not picked your donuts up in the ROTC room, please do that before you leave campus today. All donuts need to be picked up before you leave campus today. Thank you.
alright, so let's try to at least get this last one thing together. So if I have a point, one point on the graph is definitely x, f of x. And so if I have another point in the graph, and I'm just going to call it a, f of a. Okay, so if I want the slope of this line, then I could just do f of x minus f of a over x minus a. All right, that's that slope of the line. Okay, so if we look back at this picture, if I want this to be, if I want this to be a tangent line, not just the average rate of change, then I would need to move this point right here over closer and closer and closer and closer to my x value. Or I guess I could think of it, well, we could move our x. We can move our x this way. We could move our x right here. I guess that's probably what I should do. So as I move this point right here closer and closer and closer and closer over here, what does my x value approach? It gets closer and closer and closer to a, whatever that a might be, right? So if we want to know the slope of a line at any point, then we can take the slope formula right here and do the limit as x approaches a. And so I do not have time to show you any more than that right now. So you do not have homework because we